Hey everyone, I'm Xiangyun. I have to apologize. My topic is different from the abstract I submitted because I totally failed as using LSTM to predict new constructions. So I just introduced another part of my job. As introduced, I am second-year PhD student in Swansea and followed by Professor Chen Feng's supervising. And my topic is about multi-phase porous media stochastic reconstruction based on AI method. So to begin with, stochastic reconstruction has a huge difference between all the other kind of reconstruction introduced by the speakers today. Sorry, I don't know why it happens. I was now to introduce why. We can get all kinds of 2D or 3D image from X-ray, CT, or kind of other scanning. After we do all kinds of image process, the acquired digital microstructures can be done various different numerical simulations, so we can get our physical process, including pumpability, diffusivity, and conductivity, and elasticity. But due to the intricacy, stochasticity, and heterogeneous of porous microstructure, the microscopic property of certain porous media can fluctuate dramatically and have exhibited strong uncertainty. For example, this is kind of like a rock test. We do it. Sorry. This is a FEM and DEM simulation we get from another group member. This actually we fix bottom. This is an image we get from a core, and we fix on the bottom surface and load it on the top surface and get a load and displacement relationship between each other. But we can imagine if we load it on and we load and fix on the other directions, the deformation will be totally different. But this material from the large scale is an isotopic one, so the uncertainty can be shown very easily. Therefore, investigating the relationship between microstructure characteristic and microscopic property of neutral porous media can be considered as a statistic learning problem. Basically, a complete computational database of porous media goes far beyond a single representative sample and should be account for representative volume elements or statistic volume elements with all possible configurations. So what our job is that we extend the only limit available physical samples of natural porous media. So as the example showed in the left picture is a rock core, and because visualizing and digitizing the 3D microstructures through volumetric image system are technically demanding, time-consuming, and cost-intensive. So we use stochastic microstructure reconstruction to give us an effective and economical way to generate different viral samples and which contain microstructure characteristics that can vary systematically. In general, this kind of microstructure reconstruction can be divided into two characters. First is equal-dimensional one, which means 2D to 2D reconstruction, or 3D to 3D reconstruction, and dimensional updated one, which is 2D to 3D methods. To be honest, I tried to build this from 2D images to 3D images, but it's still not workable. And compare, the reason why I want to do it is just compare with 3D, I don't know why it's happened. 3D microstructure imaging is much cheaper and easier to get a high qualified 2D images. So it would be super good if we get a 2D to 3D method. So today we'll only introduce like 2D to 2D and 3D to 3D reconstructions. First, I introduce the 2D reconstruction method. It will be divided into 3 steps. First, we do the pre-treatment. We divide it into different phase image, and we get a rhythm reconstruction to train, to rebuild, sorry. And next step is we train the single phase network, and I introduce my reconstruction algorithm. And third thing is that we rebuild phase by phase, which is a cycled reconstruction method. To begin with, this is a 3-phase 2D image, we can very easy to divide it into different phases. So we can get our training label from the left figure and our feature from the right three images. So we build our random reconstruction from original one, which means, for example, we take an example, we take example, for example, if this is a 400 pixel multiply 400 pixel to the image, we can divide it into four different images, and each image was randomly picked from the original image and like merged together. But in general, we don't. In practice, we will divide it into like 1,000 different pieces and merge it together. So it was random reconstructed. And then we introduce a single phase reconstruction method. To begin with, we need to get our data prepared. If we zoom in this 2D image, we can see it is actually a pixel either B0 or B1, which is a two-phase material. So we take three radius images, which is a 7 pixel multiply 7 pixel to the image, and reshape it to a vector, and we take the central pixel is a label we need to get and set other pixels as a feature. So we use a very simple 2D two-layer hyperbolic tangent functions and use segment functions as our output. So we get the possibility of new phase. So it will be either 0 or 1 and get the possibility 90%. So it will be 90% possibility to get phase in 1. And this is a reconstruction algorithm we use. We update pixel by pixel from the left pixel to right pixel and to the end of pixel. But in practice, we just we do a parallel work. We update all this image for one time and do an integration. So say this is an image, we only update the central part. If we want to get, for example, if we want to get a 100 pixel multiply 100 pixel, we need to rebuild like 103 multiply 103 image and only get the central part. But in application, we build like very large one, only pick the central part, so it will be updated. And the problem is that if we learn to divide it into 3 different phases at one time, the whole picture will generally between one phase one. It will be either totally black picture, gray picture, or white picture. So we just design 3 different network for different phases, so we can learn with different radians. So can learn the feature in different range. So in my method, I just update one phase in one time and make a cycle. So in each pixel, it will be record the possibility in phase 1, phase 2, and phase 3. So we pick the highest possibility and update this pixel to that one. So this is our result. The left picture is original image and updated with 5 region, region 5, 15 to phase 2, 5 to the third phase, and the middle, the center part is updated. I only have like a very limited size one to show the accuracy and effectivity. And another part is a 3D reconstruction method. Basically, it's very similar to the 2D ones, except we get the data from 3D and we ship to vector and label, and we still update it pixel by pixel, but in a 3D way. So this is the result I get. And sorry, it's I didn't update the video here. I will update video in later. I should use Paraview, but it's just crack on my PC. Sorry. This is a method I designed for 2D to 3D reconstruction. It's just temporarily 3D to 3D one. And you can see when we prepare data for the training, this is a 3D image, but we can divide it into 3 2D images. This is a XY surface, YZ surface, and this is, what is it? XZ surface. So we can train with 1 2D pictures and predict from 3 2D image we get formed 3D simples. And this method only apply for isotropic heterogeneous materials. If we want to use to anisotropic heterogeneous materials, we will use 3 different networks to get the 3 directions features. And actually, I use 9 2D image in reconstructions. So we get 9, we train only 1 time for 1 phase and predict from 9 different 2D images. I should do these things. This is random noise from 1 to 0 and rebuild from the totally random noise, which help us to apply 2D to 3D reconstructions, but I failed, so I still reconstruct from this random reconstruction result. So this is a 5.5.15 video result. It's a bit slow. So I just take a video of layer by layer, obviously in Z direction and make it showing here. It's a bit fluent than before, and I admit there are a lot of white, gray, or black noise there. It's still not perfect, but it's a good method to rebuild 3-phase images. The starting point is very, can you see it's not smooth because I can't train from, I can only train central part of it. And you can see there was a black arrow at the first view layer because the black arrow is a phase 3, which used in radium 15. So it will be turned to all black at the 5 to 15th layer. And this also explains why I can't train in 1 network. And this, I also tried the different material. I don't have this. So I did not upload the video here. And also try on 4-phase material. There's a lot of noise here. I should just change the parameters here. So just work like that. And for the future work, I need to find the descriptor. Honestly speaking, we can only focus on a limited descriptor. If we want to focus on mechanical properties, we need to build a physical informed network to make it not a black box problem. Another thing is that I want to build the 2D to 3D reconstructions, and I have a dream to use LSTM. I didn't give up. So that's all I have.